Okay, so we've covered counting, including permutations and combinations. Last thing in counting is you need to know a little bit about combinatorial identities, specifically the binomial theorem. That is very useful when you're trying to count things. Okay, so for any non-negative integer n, if I take the 1 plus x to the power of n, I can actually expand that using the binomial theorem. Right? It's basically summation, k goes from 0 to n choose k times x to the power of k. Right? If you expand it, it'll be this. Remember, n choose 0 is always 1, right? And x to the 0 is 1. N choose 1 is always n. N choose 2, I could replace this with n by n minus 1 over 2 if I wanted, but I could just leave it so. And remember, it's symmetric. So if the coefficient here is 1, the coefficient at the end will be 1. If the coefficient here is n, coefficient in this term will also be n, and so on. All right, so you can actually prove this simplified version of the binomial theorem if you wanted to. The reason being, if you want to get the coefficient of x to the power of k, right? In this, basically what you do is you're taking 1 plus x and multiplying itself n times. But if you want to get x to the power of k, it's like choosing k of these x's to multiply together. And then the remaining ones will just be 1 to multiply. Right? So you're basically choosing k out of these n terms to get the number of, well, the x's that you're multiplying by. That's why the coefficient is n choose k. Right? You choose k from the n of n ones you have here. Right, this is the more general version of it. So here I have 1 plus x. I could have taken a plus b, or if you want y plus x if you want, because you already have x. So a plus b to the power of n is the summation. K goes from 0 to n. Again, n choose k is the coefficient. So what you do is you start with a to the power of k, and then you have b to the power n minus k. Right? The sum of the powers must always be n. Here in this thing. So for example, if I had a to the power of 1, then b should be to the power of n minus 1. Right? Up here, it didn't really happen because I had 1, right? So what I really have here is I really have multiplied by 1 to the power of n minus k, but I mean 1 to the power of n minus k just works out to be 1. So you just get this thing, which is simple. But this, you actually do need to know the general version, because sometimes you have to multiply things out where you don't just have a 1 plus x. You have two different things. All right, so remember these coefficients follow Pascal's triangle. So if you're not sure what the coefficients are, you could use Pascal's triangle to try to figure them out if you can't remember the formula. All right, so these things here, this is an exercise that I want you all to do. I'll give you some hints for the first couple. So with this one, if you notice, right, this looks similar to something up here. If I choose x as 1, right? If I choose x as 1, the left-hand side becomes 1 plus 1, which is 2 to the power of n. And then here, I'll just have, this is 1, right? 1 to the power of k is just 1. So that basically proves the first one. For the second one, what you could try doing is, this one is a little more complicated than this. So try to expand this and use the formula for basically n minus 1, choose k minus 1. Write it out and try to manipulate it and write it in terms of this. Right? So you know k times n choose k would be n factorial divided by, well, k times n factorial over k factorial by n minus k factorial, and then you could figure out what this is and try to show that they're equal. You'll have to do some manipulations in it. Now with this one, so once you've proven this, right, you know k times n choose k is this. So you can just substitute this into here, and we want to prove the summation of that is this. Notice this k starts at 1. So what I want you all to do is try to figure out how to prove that. So you'll have to try to use this, as I said, and you will also, it may also help if you use this, right? Because there's a 2 to the power of something there, so it looks similar-ish. So I want to see what you'll do with that. These are just small manipulations. I want to see what you'll do with this as well. Okay, so the next topic is pigeonhole principle. And there are different versions of the pigeonhole principle mentioned here. So it starts simple and then it gets all more complicated from there. So simple version. If k plus 1 pigeons are to be placed into k pigeonholes, right? So you have k plus 1 pigeons, trying to place them into k pigeonholes. So for example, let's say you have k is 3. You had 4 pigeons and you're trying to put those into 3 pigeonholes. If you think about it, no matter how you do it, if you try to distribute it evenly, there'll be 1 pigeon in each hole, but then there's an extra pigeon, which has to go into one of the holes as well. So there would always be a hole containing 2 pigeons. Right? If the number of pigeons is more than the number of holes, then there's at least 1 hole containing 2 pigeons. Right? Well, actually, what I said is a more generalized version. So this is just if you had k plus 1 and k, but if you think about it, if you had more than k plus 1 as well, so if you had k plus 2 or k plus 3, or in fact, as long as you have more than k pigeons and you're trying to place those into k pigeon holes, there will always be at least 2 pigeons in one of the holes. It's possible that there will be more than 2 pigeons in a hole, or it's possible that there are 2 holes containing more than 2, at least 2 pigeons. But what the theorem says is that there is at least 1, right? At least 1 pigeonhole containing at least 2 pigeons. So it could be more. All right. Further generalization is, so this was more than k pigeons trying to go into k pigeonholes. Now we have more than m times k pigeons, again trying to go into k pigeonholes. Right. So for example, suppose we had more than 2 k pigeons trying to go into k pigeonholes. If you try to distribute those as evenly as possible, then you'll get 2 in each pigeonhole, and then you'll get an extra pigeon that has to go somewhere. So there'll be an extra 1. So there'll be, if m was 2, you would have a pigeonhole containing 3 pigeons. So whatever m is, there'll always be m plus 1 pigeons in at least one of the holes. Right. What I want you all to do as well is try to. These are very easily proven using proof by contradiction. So I want you all to try to prove those. This one as well. This is the, well, these, I guess, are the fully generalized versions of the pigeonhole principle. So if you had more than n pigeons and you're trying to place those into exactly k pigeonholes, then there's at least 1 pigeonhole containing at least the floor of n choose k plus 1. Right? So you have more than n pigeons. So basically what you're trying to do is find the smallest multiple or the largest multiple of k that is less than n, and that would be given by this. Right? And since you have more than n, there would always be an extra pigeon. So that's why you add 1. Now if you had exactly n pigeons, right, then you actually have 2 cases to consider. So if it's exactly n pigeons and you're trying to place those in k pigeonholes, suppose first that n is not a multiple of k. If n is not a multiple of k, so then the answer again would be floor of n choose k, n over k, sorry, plus 1. But if n is a multiple of k, then this is not necessarily going to be true. If n is a multiple of k, then the answer is just n over k. Right? Actually, there's a way you could kind of combine these two. If it was exactly n, you could take it as floor of n minus 1 over k plus 1, and that would cover both cases. If you kind of compare it to the one up here, right? Using the idea from this one, you could use that down here to combine them if you wanted to. All right. So yeah. So I want you all to try to prove all of these by contradiction. All right. Let's see how this works now. So in a group of 8 people, show that in any particular year, at least 2 have their birthday on the same day of the week. So we have 8 people. Doesn't matter which 8 people. We just choose 8 people at random. We want to show that in any particular year, for example, this year, at least 2 of them have their birthday on the same day of the week, meaning either Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So notice there are 7 days of the week, right? But we have 8 people. So according to the pigeonhole principle, we have 8, you can think of the people, in this case, the people would be pigeons. So you have 8 pigeons trying to go into 7 pigeonholes. So there must be at least 1 pigeonhole containing 2 pigeons, or 2 people in this case. Right? Because even if you try to distribute them evenly, you would get 1 in each, and then there's an extra 1 that has to go somewhere. Okay, three numbers are chosen at random. Their sum is 19. Show that at least one number is 7 or more. So three numbers are chosen at random and their sum is 19. So you want to show that at least one number is 7 or more. So I say equivalently, you want to put 19 pigeons into 3 pigeonholes, right? Because basically you can think of this as 19 ones. So you have 19 ones and you're trying to separate those into 3 numbers. So 3 pigeonholes. So by pigeonhole principle, there's at least one containing basically 4 of that 19 divided by 3. 4 of 19 over 3 would just be 6, right? Because 19 divided by 3 would be 6 and a third. So 4 of that is 6, plus 1 would give you 7 pigeons. That's one way to do it. You could also try to do this by contradiction. So you could assume that all the numbers are less than 6 and then see what happens with that. All right, a box contains 10 French books, 23 Spanish books, 8 German, 16 Russian, and 19 Italian books. How many must we choose to ensure that we have 12 books in the same language? So we basically want to choose the minimum number of books that we can choose to guarantee that we always have, we will be able to find 12 books in the same language among those we've chosen. Now, when you're doing this, note that there are 10 French and 8 German. Those are less than 12. So we can never get 12 German or 12 French. So when we count in this, we're going to have to assume that these 10 and these 8 are included because it's possible to include them and not have 12. All right. This isn't really pigeonhole principle, it's more kind of logical, but you could see how it works if you think about it from the pigeonhole point of view. Right, so you must have, if you want to have 12, right, you must have 11 and an additional 1. All right, so 2 of them take less than 10, 11, so that's these 2. All right, so you need to include those, and then you include 11 Spanish, 11 Russian. Now you're not including 12, right? Because if you include 12 of this and 12 of that and 12 of that, you're overcounting because we just want 12 in any language. So if I included this 10 and this 8 and I include 11 of these, 11 of these, and 11 of these, and then I choose any random book to add to that, the other book I add will be either a Spanish or a Russian or an Italian, right? And then whichever one it is, that language will have 12 books. So that's all I need. I don't need to include a 12th one here and here and here. It's just one of those. So the answer works out to be 52. All right, I want you all to go through these questions. Please try them. Give it as much time as you can. Pigeonhole principle is actually something that is very, very, very important in combinatorics questions. It may not be obvious how to apply it. Like there are some questions, especially the more complicated ones, where you would not even think you could use pigeonhole principle to solve it, but it can be used in some very creative ways. It could even be used in some geometry problems as well. So consider this question down here. All right, so try these problems. All right, the 3 other things we're going to talk about. We wouldn't spend as much time on the remaining ones because there isn't much theory behind them. So the first one is the invariance principle. Now, an invariant is just some kind of property something that doesn't change, right? Invariant means it doesn't change. So basically what we're doing is in any question, in some questions we're given, sometimes we can identify properties that don't change. So for example, the parity of some numbers, if you do let's just say the question has some procedures you do. It might be such that throughout the procedure, the parity of certain numbers doesn't change. Or it might even be mono-invariant, right? So throughout the procedure, you might see that the sum of the numbers keeps decreasing or something like that. Mono-invariant means it only changes in one specific way. So in that case, it would be decreasing, meaning it only goes down. It doesn't alternate or go up. right? So you should also look out for things like that, invariance or mono-invariance, because those can help you restrict the possibilities of what can happen. There are two simple examples here. I used to have a third example in this, but it is very complicated to see how that works. So I left it out. But we could look at that later on at some point. So two diametrically opposite corners of an 8x8 chessboard are deleted. Is it possible to tile the remaining 62 squares? Remember, 8x8 will be 64, so you remove the any two diametrically opposite corners. That leaves you 62 squares, and you want to tile those with 32 dominoes. Now, a domino will cover two spaces, right? 2 by 1. So technically, these will cover the same, these will cover 62 squares as well. And you have 62 squares to fill. The problem is that it doesn't actually work, right? So notice if you look at an 8x8 chessboard, if you color the squares like alternating red, black, then in the 8x8 board, there'll be 32 of each before you remove the corners. Now the two opposite corners, if you actually look at it, will have, if you do the coloring and look at it, will have the same color, meaning that they will either both be red or both be black. So when you remove those two, you're removing either two red or two black, meaning you're changing the number of red or black. So we could say without loss of generality, suppose you remove two red. It means that now there will be 30 red squares and 32 black squares. But one thing to note is that a domino it covers two adjacent squares, so it must cover a red and a black. So it means that no matter how you tile this thing, there will always be two black squares remaining, right? Because they are more black, they're more black than red. Since this covers an even number of black and red, it will always leave two black ones remaining. And actually things like that, when you have grids or boards to look at, coloring things usually helps, like coloring it like this, red or black. Sometimes you might need to, so if you think about it, red or black is really just talking about parity, right? So you could think of it as adding a 1 or a 0, right? And you could actually extend that further. Some questions you have to go 1, 0, 2. I'll show you a couple examples of that just now. Right, next example, the numbers 1 to 10 are written in a row, show that no matter what choice of sign plus or minus you choose, the sum will never be 0. Right, this is a straightforward one. If you look at the numbers 1 to 10, right, the sum is 55. That's an odd number. Now, suppose I had changed this plus 2 to a minus 2, right? Remember, changing the signs. If this plus goes to minus, then the difference, well, the number will become, instead of plus 2, I'll have minus 2, so I'll actually get 51. Right? And actually, that's even if this plus 3 was changed to a minus, I'll be subtracting 6. Basically, you're subtracting twice the number you would have had here. So it's always subtracting an even number when you include a minus sign. Meaning that you don't change the parity is invariant. Right? So since the initial number is 55 is odd, you could never get an even number, so you could never get 0. All right, I want to show you something what I meant with the coloring, because that's important to know. So I'll skip ahead. Let me see if I can find the question. This is a miscellaneous exercise. Just note this question is repeated from the exercise above, so you'll see the same thing there. I think it's near the end. Okay, it's probably better if I look at the solutions and try to find this. All right, so looking at questions 26 and 27, both of those use the idea I just talked about. So 26, Determine whether it is possible to tile a 10 by 10 square floor using 1 by 4 rectangular tiles. So note that the sum or the number of squares in a 10 by 10 floor is 100. Technically, this covers 4. 4 is a factor of 100, so you might think it might work, but it actually does not work. And to show that, I wouldn't do 27. I'll leave that for you all to work on. So 1, 2, 3, 4, 5, 6, 7, 8, 4 and 4, 8, 10, 4 and 4, 8, 10. So this is basically 100 numbers I have here. So what I've done is I've numbered those squares. So the first square is 1, 2, 3, 4, then 1, 2, 3, 4, and then 1, 2. It's only 10 here, so I have to stop at 2, right? And the second row, I'm going to number it like this. This is just how I choose to number it. You could actually even think about this as colors if you wanted, but you would need 4 different colors. So it's better to use numbers so that it's easier to see what's happening. Right, so we do that. We go 1 to 4, and then we repeat that, and then we start. We do it this way as well. And then because I started with 2 here, I have to go 3, 4, 1, 2, 3, 4. You always go in order. Now, note that no matter how you place a 1 by 4 square in this based on the numbering, it will always cover one of each of the numbers 1 to 4. So for example, if I started here, 4, 1, 2, 3. If I started here, 2, 3, 4, 1. If I do it vertically here, 2, 3, 4, 1. I've chosen a numbering so that it always covers one of each of the numbers, right? It means that the only way that thing could tile this is if the number of 1s is the same as the number of 2s, which is the same as the number of 3s, and the same as the number of 4s. Because each one of the tiles covers the same number. So it covers one of each. Right, so what I mean is that if I had more, for example, if I had more 4s than I had 1s, then there's no way it could cover all of them because there will be a 4 left that can't be covered. Right, now if you count this, well, there isn't an explanation, but if you count this, right, you will see that the numbers don't add up, right? There are more of certain numbers than others. So basically, if you consider this 2 by 2 square down here, everything apart from this will work out. Right, so so you could think about it this way: 1 to 4, 1 to 4, right? 2 to 1, 2 to 1. Well, they are the 4 numbers in each of these rows. Ignore the last 2 columns and the last 2 rows. We'll check those after. Within this 8 by 8 square, there's an even number of, or the same number of all of the 4 numbers. Then here I have the numbers 1 to 4, 1 to 4, and then same thing here. Same thing here. So I'm left with this 2 by 2 grid. Same thing down here, 1 to 4, 1 to 4. So it's only down here that I have to worry about. Now I have 1, 2, 3, and I would need a 4 for this to work, but I have an extra 2. So basically what happens is I have 1 extra 2 and 1 less 4, which means that I cannot actually do what I want to do. So that's why the answer is no. All right, and you kind of saw what happened below. Question 27 looked at a similar idea for how to do the proof.
Jax, when you're doing the proof for that, right?
Yeah.
When you said how a 1 by 4 square takes up one of each number, right? Do you have to show that, or is it just trivial to see?
You could just, because it is true, right? You could just say based on the numbering, that is what happened, because that is how you've defined it. And it will happen as long as you number it like this. So you go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, and then the number here. So you number the first row so that it works, and then you number the first column so that it works, and then you start from there and you keep going in the same order. Once you keep the same pattern repeating, it will work. It doesn't matter if it was 4 numbers or 5 numbers or 2 numbers. As long as you do that pattern, it always works. That's not something you would have to prove. That is something more like you could just look at by observation. All right, so that is what I wanted to show you there. So we'll come back to this. All right, so try this question. You already saw the answer. The answer is no, so you have to try to figure out how to do it using a similar idea. All right, so pigeonhole and invariance, we covered those. I want you all to try these questions as well. This is a nice question, but unless you figure out, it's a weird invariant. Unless you figure out what the invariant is, you're not going to be able to solve it. Right, so you have to just look at different things and see what happens. The key is to try to figure out what the operations let you do. All right, next topic is game theory. Now, game theory doesn't have much theory behind it based on what we do actually. It's basically just looking at what happens when you have games happening between two people, or maybe more than two people sometimes, and trying to see if there's a strategy that someone can follow to win. Now, when you're talking about game theory, we always assume that everybody plays optimally, meaning that if there's some loophole where if this person does something stupid, they're going to lose. They're not actually going to do that. They will, if there's a way to stop the other person from winning, they will always do it. Right? So never fall into the trap of saying, well, maybe this person doesn't make the move to stop the other person, so they lose. That doesn't happen. Right, example 28. Players A and B play a game as follows. First, A says either 1, 2, or 3. B can add 1, 2, or 3 to that number. So for example, if A said 2, then B can either add 1, 2, or 3. So B can either say 3, 4, 5. And it keeps going like that. So it continues where the other player will keep adding either 1, 2, or 3 to the previous number. So for example, A can say 2, then B can say 5, and then A could say 6 or 7 or 8 if they wanted to. And then so on, they keep going, and the player who says 100 wins. Who has a winning strategy? Well, so there's an explanation here that says B has a winning strategy. So whenever A adds a number X to the previous number, then B should add 4 minus X. So even though A goes first, B has the second person who plays in this game has a winning strategy. So suppose A added X in any turn, then B could always add 4 minus X, right? And if A adds X and then B adds 4 minus X, the overall outcome of that round will be that after the two of them played, the number 4 is added to whatever was there from the round before. So if they keep doing this, right? For example, if A says 1 at the start, then B says 3. If A says 2, then B says 2. If A says 3, then B says 1. Then at the end of the first round, the number will be 4. And then it keeps going. So basically what that means is that every time B finishes, the number is a multiple of 4. And since 100 is a multiple of 4, it means that B is the only one who could say that. So that's the strategy that B would have to make sure that whatever number he says is always a multiple of 4. So that way he guarantees that he could say 100. And also if he's the one that says a multiple of 4, then A could only add 1, 2, or 3. So there's no way that A could say a multiple of 4 after that, as long as B plays optimally. So A has absolutely no way of winning this game. Now I want to ask you a question. Suppose the player who said 100, suppose they go up to 100, they're not allowed to exceed 100, and the player who says 100 loses. Who would have a winning strategy in that case? So similar game, but the person who says 100 loses, and they're not allowed to go above 100. So another way you can think about it is the first person who says a 3-digit number loses.
Yeah, A would win because he just has to keep it at 3 mod 4. So if he starts by saying 3, whoever B says, he just adds on 4 to that. So he goes like 3, 7, and he'll hit 99, I think.
Yeah, that's correct. So basically, how you're looking at it from this point of view now is that essentially the person who ends up on 99 is going to win, because then the other person has to say a 3-digit number. So trying to see who could guarantee that they end up on 99. Now, since A plays first, he would have the first choice of trying to get to 99. And since you're right, 99 is 3 mod 4, then he just has to say 3 on the first turn, right? So he must say 3 on the first turn, and then whatever B says, he just says 4 minus that number. and then he will always end up 3 mod 4, so he will always end up on 99, and then basically B will lose. That's good. All right, next example here, consider a row of n greater than or equal to 3 chairs. Suppose that 2 children are sitting in the 2 chairs situated at the ends. Alternately, the 2 children move either 1 or 3 places towards the other one until one of them cannot move anymore. They can't cross each other, right? So once they get adjacent to each other, that's it. The one that cannot move loses. Determine the conditions necessary for each child to win. So you could think of the first child being on the left and then the second child being on the right. So you could think of it that way here. It isn't clear there, I think. Right? I guess you could think of it as being symmetric. So whichever one plays first, you could call out the first child, or whichever one moves first. Right, so note that after each child's turn, the number of chairs between the two of them is reduced by an odd number, right? Because it's either 1 or 3 spaces they're moving. So therefore, the parity changes each turn because the parity of the number of chairs between them, because you're always reducing by an odd number. So before, if it was even, now it will become odd. If it was odd before, now it will become even. So this is a mono invariant, right? It always changes the same way. So if there was an even number of chairs, then it would be odd. Right? What was it? So then before the second child moves, each turn there will be an odd number. Right? If there was an even number at the start, then the first person who moves gives you an odd number between them. So before the second child moves, there's always an odd number. It means that that child will always be able to move because there's always an odd number of chairs between them. Right? And since 0 is even, it's not possible for the number of chairs between them to be 0. Right? The second child will therefore always win, and because of this, because at the end of it, the first child will be the one left with an even number of chairs before their turn. So it's the first child who will always be in a losing position. But if n is odd, right? If there's an odd number of chairs, then the opposite happens. So the first child will always win, because it means after the first child's turn, there's always an even number of chairs between them, and eventually it'll keep reducing until they get to 0, and the second child will not have a chair to move to. Right, again, more questions there for you to try. Now, double counting, I'm just going to briefly go through this before the 5 minutes up. So double counting is basically where you count something in 2 different ways. And that lets you either create inequalities that let you kind of identify what values certain things could be, or it lets you basically it lets you identify certain properties that change in only certain ways. There's a typo here that kind of threw me off. 15 students did a summer course. Each day, 3 students were on duty after school to clean the classroom. After the course, it was found that each pair of students had been on duty together exactly once. Each pair was exactly once on duty. How many days does the course last for? That's a typo. Right, so let that number of days be k. So assume the answer is k. We can count the total number of pairs of students who are on duty together, right? Because each day, 3 students were on duty, right? Right, and also the other one is each pair of students was on duty exactly once. So if you had 15 students and each pair of students was on duty exactly once, it means that the number of pairs that you're gonna have of students on duty is this, it's 105. Right, on the other hand, 3 students were on duty each day. So each day had 3 students. So this number, which is the number of pairs, is also equal to, remember, if you have 3 students on duty each day, it means you have 3 pairs, 3 to choose 2, which is 3 pairs each day, right? Because, for example, in the first day you have 3 students on duty, that gives you 3 pairs. You take AB, AC, and BC. And then each day you have 3 pairs, right? So it's K days times 3 pairs gives you the total number of pairs you can have. Now this total number of pairs is also given by this answer, this working here, which is what we counted in a different way. So we counted the number of pairs one way, we counted it a second way, and then since it's the same thing we are counting, they must be equal. So K must be 35. That's how you find the value of K. All right, second example, usually double counting is a lot more complicated than this. This is a simple example. So at a party with 11 people, every person claims that they shook hands with exactly 5 other people. Show that someone is lying. All right, so what we're gonna do is give each person a label from 1 to 11. There are 11 people. And we're gonna label the handshakes from 1 to n for some value of n. Suppose there are n handshakes, so we start at 1 and label them. So consider the pairs IJ, where person I participated in handshake J. So IJ basically is a pair where the first number is the person and the second number is the handshake. So we're gonna count the number of these pairs in 2 different ways. First, each person participated in 5 handshakes. That's what it said. Each person took part in exactly 5 handshakes. So for each I, there's 5 values of J possible, right? So since there are 11 I and there are 5 values of J for each one, the total number is 11 times 5, which is 55. On the other hand, each handshake involves 2 people, right? So for each J, there's 2 values of I, right? And we know there are n handshakes, so J goes from 1 to n. So for each of those, there are 2 possibilities for I. So the answer here would be 2n. Right? And again, this is the same thing we counted in 2 different ways. It means that 55 must be equal to 2n, which is a contradiction. So somebody is lying because this is odd and this is even. This here is more along the lines of how you do a double counting, right? You normally have to label things. So you count pairs or you count triples or something like that. You don't just count something straightforward like this. This is a simple version. So in these questions out here, exercise 33, you might have to look at the solutions. The first one might be straightforward. The others, especially these 2, are very complicated. So yeah, you could spend some time and go through those. Double counting is something that can very much come in an IMO problem. So it's something that you should know. Now, along with double counting, there's something called incidence matrices, which can be used. I'll ask Prasanna to kind of go through that with you all, because he understands that much better than I do. Right, yeah, and that's it. So I want you all to try these questions. Most of these questions are doable, unlike the number theory ones at the end. It's only questions, well, the IMO ones, maybe questions 38 onwards tend to get a little hard. Okay, any questions?